Okay, so last time we started to discuss basically how we can do some kind of a 3D reconstruction using the multi-view images. And that was basically the idea. Even without like using any neural net, any neural deep learning kind of things, we just like do some kind of the calculation in terms of like finding the 2D correspondence and also calculating the camera, the model, the camera, the matrix based on that, and also finding some kind of 2D to 3D correspondence and doing some kind of the optimization. And we started discussing the very basic idea in terms of like how we can do some kind of the calculation of the camera model based on the 2D correspondence to information. So we started to discuss the basic idea, which is called the epipolar geometry, while introducing some kind of the new terms. Right? So I hope you remember the things that we discussed last time in terms of some kind of the definitions of like the epipolar line or the epipole. So epipolar line was basically the corresponding the line of the 2D point in the other image. So when you think about like having the two multi-view images like this, like having the first one the left-hand side and the second one the right-hand side, when you have like one point in the first image, depending on like what was the 3D point that has been projected into this point, we can basically draw a line, which is basically showing some kind of projection of the 3D point here into the other view, right? So depending on like what was the exact 3D point along this way, we are basically also drawing this kind of some line which shows some kind of the projection of that ray. Which was called the epipolar line, corresponding to this specific point in the other view image, right? So we're having this point and the line here, and the epipole was basically the point where all the epipolar line basically passes through. So if you do like any epipolar line with the point here, whatever the point that you have, like all the epipolar lines should basically have should pass through this specific point, which is the point is called the epipole, right? Actually, we also could say that this point should be the point where the origin of the camera coordinates is basically being projected into this image plane. So that was basically the point that we call the epipole, right? So there are basically a couple of things. Like basically, this point is the projection of the origin of the camera coordinates to this image plane, and this is also the point where all the epipolar lines are basically passing through, right? So this was kind of the definition. And then based on those kind of things, we started to discuss the fundamental D matrix, which is basically defining some kind of the correspondence across the 2D points, the 2D image plane, which was defined as kind of 3x3 matrix. So we have seen that these should not be full rank matrix. It should be rank 2 matrix, right? And actually what this matrix also means is that this is basically mapping the point in the one image into the corresponding the epipolar line in the other image. So basically the mapping could be basically expressed as kind of the form of the matrix vector, the multiplication like this. So it's make it very convenient to like, describe all the things with some kind of just matrix and the vector, right? And also we could have seen that, the opposite, the kind of direction, like, so the mapping from the first image to the second image is like represented with the fundamental matrix F here. And the other way around, from the second image to the first image, this mapping could be also represented with the transpose of the same D matrix. So that was a thing that we discussed last time. And based on that, actually what we also could see is that the epipole in the second image could be calculated as the left null vector of this matrix, because we know that like all the epipolar line for whatever the point that we have in the first image, all the epipolar line, these should be basically passing through the epipole here, which means that the dot product between these, let me change this, the laser point here, yeah. So the dot product between the epipole, the coordinates here, and this should be 0, regardless the choice of the x here, which means that the epipole should be basically the left side of the null vector of the f here, and also the epipole of the other image also could be obtained by as the right null vector, right? And the same thing also could be defined with not the image coordinates, but the normalized 2D coordinates, which is also defined with the so-called default camera with the focal length of the 1 and also the no shift in the image plane, right? For this case, we could also define the same thing in the same way. The only difference with the fundamental matrix and the essential matrix is that this essential matrix does not involve any kind of the camera intrinsic parameters, while the fundamental matrix is defined based on the intrinsic parameters that we should have for each of the camera. Right? So the relationship between the essential D matrix and the fundamental D matrix is defined in this way. So if you basically multiply the intrinsic the camera intrinsic D matrix, the transpose and the matrix itself on the left and the right hand side of the fundamental D matrix, based on that we can directly calculate the essential D matrix. And the other way around is also the same, right? So this was kind of the relationship between the fundamental matrix and the essential D matrix. And our final goal is to basically calculate the camera model, especially the extrinsic parameters, when we assume that the intrinsic parameters are given. Like estimating the intrinsic parameters is kind of like another kind of big thing, but we're going to assume that it's kind of the given. So given the intrinsic matrix, how we can basically calculate the extrinsic parameters. And for that, actually, we also discussed like how we can see some kind of the relationship between the essential D matrix and also the camera model, the extrinsic parameters, the rotation and the translation. And for that, basically, what we are going to do is that we are going to set the camera coordinates of the first image as kind of the world coordinates. So the rotation translation for the first camera is basically identity and 0, because like we set the world coordinates in that way, right? So in this case, basically what we can see is that basically the epipole was the projection of the origin of the other image to the image of the second image plane, right? And now we set the world coordinates to be the same with the camera coordinates of the first image. So the epipole actually can be computed by projecting the origin of the world coordinates with the extrinsic parameters of the second image, right? That should be the epipole, the normalized coordinates of the epipole. Right? So the normalized coordinates of the epipole can be calculated in this way, which shows that actually it should be just the same with the translation part. While so it's kind of not exactly the same in terms of that this is the homogeneous coordinates in the two-dimensional space, while this is the translations, the 3D, just literally like three-dimensional vector representing the translation in this 3D space. If you just treat this like translation vector in the 3D space as kind of the homogeneous coordinates in the 2D space, that becomes the normalized coordinates of the epipole. Right? This is like how we can calculate this. And one more thing is that if we see the epipolar line of any of the point in the first image here, with the x hat here is basically any point in the first image with the normalized coordinates. Then what we can see is that this epipolar line actually can be calculated in this way, in this form, by definition of our essential D matrix, right? So the epipolar line can be represented this way, and we know that this epipolar line should pass through the 2 points, the corresponding point here, and also the epipole here, right? So the corresponding point can be also computed by multiplying the extrinsic D matrix, and we have seen how we can calculate the epipole here. So if you take the cross product between these two, then what we can say is that actually the essential D matrix should be the same with this form, the multiplication of the skew symmetric D matrix of the translation part here, and also the rotation. So what we can see here is that this basically shows some kind of the relationship between the translation and the rotation, that this is something that we want to really get, right? Finally, we want to get the translation, the rotation with respect to the first image, which we set as the world coordinates. But actually, from the essential D matrix, actually we can decompose the translation part and the rotation part. And we're gonna see how we can do this kind of decomposition. Any questions on this? So this is some kind of the relationship, of course, some kind of the terms that we just like define. Click. And because of the fact that the essential D matrix is like represented as kind of some multiplication of the skew symmetric D matrix and the other, what we can actually see is that the essential D matrix should be not the full length D matrix, but the rank 2 matrix, because this skew symmetric D matrix is also the rank 2 matrix. And it's also the same for the fundamental D matrix as well, because like the fundamental D matrix is also kind of the multiplication deform with respect to the essential D matrix, right? So it's basically having some kind of the another some kind of the constraint for the matrix that we are going to calculate. So basically, we know that both the fundamental D matrix and the essential D matrix, both of them have the scale ambiguity, right? Because like all the kind of the coordinates that we are multiplying to this matrix are basically homogeneous coordinates. So it doesn't matter like what sort of the scale that non-zero scale that we multiply to these matrices, which means that there are the scale the ambiguity. And also the constraint is that the rank of those matrix should be 2, which means that the determinant should be 0. So these are also adding some kind of another the constraint for those two the matrices. Make sense? Clear? Any questions on this? So basically what we are going to do is that, let's say we detected the key points on all the multi-tube images, and we found the correspondences using some kind of the features which of the point. So we didn't discuss any details for that, but we are basically using some kind of the some off-the-shelf tools in terms of defining some features for the key points and basically find some kind of correspondences. So let's say like these kind of the 2D correspondences are like given. So based on that, what we are going to do at the end is basically calculating the relative the camera the matrix, the camera pose. The rotation, the translation when you set the camera coordinates of the first image as the world coordinates. Make sense? And we are for that, like we want to basically take some kind of bunch of the steps. The first step is basically to calculate the fundamental the matrix based on the key points. And based on the fundamental D matrix, if the intrinsic D matrix is basically given, then we can directly calculate the essential D matrix, right? So we have seen how we can do this. And based on that, like once we get the essential D matrix, now we want to decompose this into the rotation and the translation. So these are some kind of the bunch of the steps in terms of getting the final, the rotation and translation. Clear? So all these of the steps here are basically involving some kind of some sort of the linear algebra. So we are not going to get into that much kind of details for that. Yeah, but we'll see. So basically, how we can calculate the fundamental D matrix is kind of similar with like what we also have seen with the direct the linear transformation the algorithm for the camera resectioning. But now we are having slightly different form in terms of that the fundamental D matrix is basically defined in this way, multiplying the homogeneous coordinates on the left and right hand side, and the output should be 0, right? So what we can see is that now, similarly with the linear transformation, we are also making some kind of the homogeneous linear system for each of the pair, right? So what we can see is that every pair, single pair of the 2D points are basically making one equation, one homogeneous linear equation like this. So what we have seen last time is that we are having the 8 degree of the freedom in terms of that we are having the 9 elements, but having the scale ambiguity, which means that at least we need 8 equations. At least we need 8 the corresponding points. So that's why this whole algorithm is called the 8-point algorithm. So based on the 8 the corresponding points, we make at least like the 8 equation of the homogeneous linear system, and we find the kind of the final the output, the fundamental D matrix here. So we can see that this is kind of the vectorized form of the fundamental D matrix, right? So we calculate, we find the non-zero solution for this system using the SVD. So that's exactly the same that we discussed last time. So we can find the non-zero solution in the same way by solving the homogeneous linear system, very kind of similar the idea. The only thing is that we have one more the constraint. The constraint is that the output matrix should not be full rank. Its determinant should be 0, right? So that's basically another some kind of constraint. So which means that if everything is like perfect, if we have the perfect 2D correspondence, perfect the intrinsic matrices, if everything is basically perfect in terms of that there's like 0 noise, then the output would be basically the case that we're gonna get the output that is basically satisfying the condition that the determinant is 0. But if we have some kind of some small noise into either the intrinsic matrix or the 2D correspondence, then the output, the non-zero solution that we are getting from the SVD may not be basically the case that the determinant is basically zero, right? So what we can do, so there are a bunch of things that we can do, but is that given the solution that we found using the SVD by solving the homogeneous linear system, we can just like find the closest the matrix, 3 by 3 matrix, which determinants become zero. So let's say like when the F is basically the non-zero solution that we computed by solving the homogeneous linear system, we can find the other one, which is the closest one to this, while that satisfies the condition that determinant is zero. So how can you find such kind of the matrix? So without getting into any details, how can you find this is basically also using the SVD again. Simply what we can do is that once we decompose the F using the SVD in this way, if you make the smallest singular value to be zero, then this kind of the new matrix becomes this matrix, minimizing this difference while satisfying this condition. So I'm skipping some details in terms of how, why we get this kind of the solution, but that's kind of the way that we can calculate this. Okay. But you can see this is kind of like without like discussing any details about the linear algebra, in terms of like just the calculation, you can see that it's like quite simple, just applying the SVD twice with the number of the correspondences. Clear? So yeah, so this is kind of like simple. And like given this kind of the fundamental D matrix, what we can do is that given the intrinsic D matrix that we know for the images, we can just like multiply these matrices like this in a way that we are basically getting the essential D matrix here. So here also the thing is that we are now just simply assuming that the intrinsic D matrix is the same for all the images. But actually, there can be some cases that the intrinsic matrix can vary depending on the images. So especially for the example that I think I've shown last time, that we are like collecting all the internet images of the city of the Rome to reconstruct the entire city. Depending on like which devices that we used for those photos, the intrinsic matrix for each of the images will be different, right? Then you need to see like what's the kind of intrinsic matrix that we need to multiply for here. The intrinsic matrix that we are multiplying here can be changed depending on the images that we are using. Right? So this is kind of one important thing that I skipped in the slide. But anyway, so basically by multiplying the intrinsic matrix, we can get this like essential D matrix here. But the thing is that from this, we need to basically decompose this into the translation, the rotation. But also we are basically having some kind of the constraint in terms of that. If we see this Q-symmetric D matrix, so this is basically the case that we are having some kind of constraint in terms of that our essential D matrix also should satisfy this extra D condition. In terms of that, this Q-symmetric matrix basically has some two equally singular values, and while the other one is basically zero, which means that our D matrix also should have the same D constraint. So which means that we given the essential D matrix that we calculated from the fundamental D matrix here, we also need to find the E here, which is satisfying all this kind of condition, and also decomposing that matrix into the form of the translation and the rotation. So there are also like lots of the details in terms of like how we can do all the things without like discussing all the details here. What actually we can do is that given the essential D matrix that we calculated from the fundamental D matrix, if we also decompose this into the SVD again, so we are using the SVD multiple times, and define the W matrix in this way, then actually there are four possible decomposition that we can decomposing the essential matrix E here into the translation and the rotation. So when you have the U sigma V transpose like this, the rotation can be defined either as the UW transpose, here the W is basically this, or UW transpose or V transpose. So there are only two options in terms of like getting the rotation from the given the essential D matrix. And also for the translation, there are only two options, whether taking the singular the vector of the U here corresponding to the smallest the singular the value, it can be plus U3 or the minus U3. So you can see that there are only two options for each of the rotation and the translation, and the combination of like all those kind of things are making four possible the decompositions of the given the essentiality matrix. Right? So it sounds like still there are some kind of ambiguity. So once we get the kind of essentiality matrix, still there are kind of the four possible cases that we can define the and the rotation and the translation, right? So that's kind of the problem. But what we can say is that if we see all those kind of four possible cases, there is like only one case. The corresponding the 3D point is in front of the both of the cameras, which means that when you shoot the ray should be basically shooting into the z-axis, right? The g directions, not the minus g directions. So there are only kind of the two cases that both of the images are basically shooting the rays into the 3D point that we have. So while we have some kind of the four possible cases, there is only one the case which basically physically makes sense. So based on the viewing directions of the rotation and the translation, that we can choose that specific case. So this is kind of some very rough introduction in terms of like how we can do this kind of like calculation of the rotation and translation based on the 2D correspondence. So I skipped many details here because of the lack of time. For the people who want to learn more about some details for this, I strongly recommend check out this book, the Multi-View Geometry, which is the textbook. This textbook basically includes everything about like this like structure from motion, the idea, and like including all the topics that actually can be discussed over the entire semester. So I just like compressed all the things into the 1.5 kind of lectures in this course. So check out more details in this textbook. And the summary is that so basically what we are doing is that we are first like identifying the correspondence of the 2D key points. And based on that, we are using the 8-point algorithm by basically using the SVD to calculate the fundamental matrix. And also we kind of like find the closest valid fundamental matrix, which has the rank 2, the kind of form, using the SVD here, right? And given the intensity matrix, we can now calculate the essentiality matrix. And then we can also do some kind of projection with the valid the matrix using another SVD. And then now we can decompose the essentiality matrix into the form of the rotation and the translation. And there will be 4 possible cases, and we can pick the only one, the valid the pair. So this is kind of the procedure in terms of how we can get some kind of the camera model from the given the 2D correspondences, which will be also kind of the basic kind of steps for the neural rendering that we're also going to discuss for today. Any questions on this? So it sounds like now we can do like all the 3D reconstruction only with the 2D images and the correspondence without involving any deep learning things like no neural nets. So sounds is quite interesting, right? But actually kind of the thing is that while this kind of the procedure, the kind of framework can be good in terms of that we estimate all the camera the matrix and see where the images are placed in the 3D space, and we can also get some kind of the rough reconstruction of the 3D kind of things. The thing is that we can only get some kind of the 3D point of the key point that we have. Actually, there are some very recent techniques how we can also do this kind of things without like doing this kind of calculation. But for like all the non-neural net kind of techniques that have been developed for the decades, kind of the limitation is that it can be good to reconstruct some kind of structure of these 3D things. But in a way, in terms of that, when we want to not only like getting some 3D structure, but want to render things into the realistic 2D images, still we are getting some kind of some sparse points over the images, not really getting some kind of the realistic 2D images. So what the main topic that we are going to discuss for today is doing something like this. I'm not sure whether the video can be played. Oh, yeah. So while we are having just like few set of the multi-view images, can we do some kind of the like novel view synthesis, which basically means that for any kind of the arbitrary camera pose that we have in the 3D space, we just want to not only just projecting some sparse 3D key point into that image plane, we want to get really, just realistic the image like this, okay? Just like getting some kind of the image from the any arbitrary view. So it's more than doing some kind of the 3D construction. It's obviously more than just like estimating the camera pose for the images, but doing some kind of the more like denser, some kind of the 3D reconstruction. And this is kind of the part that we need to basically use some kind of the neural network here. So that's the main idea here. So let's basically see how we can achieve this kind of the idea. Let me switch the slides. Yeah, can everyone see my slide? Okay. Is everyone okay to see my slide? Okay. Yeah, so this is kind of the main topic, and this might also one of the most interesting part in this course. So if we just like come back to the roadmap of the course, we have seen some kind of the ideas about like how we can utilize the point cloud representation in terms of making the encoder and the decoder, and especially the reconstruction. We have seen that like just like getting this point cloud may not be sufficient for the many applications. So how we can do some kind of more precise the reconstruction with the implicit representation. So that was also the idea that we have discussed last time. And here, basically, what we want to do is that now we want to see how we can also do some like reconstruction of the 3D into the form of the implicit representation, but actually while taking the multi-view images as the input. So actually, it's involving both the encoding and the decoding in terms of that we are basically, the input becomes a set of the multiple images, and the output actually becomes the impulsive representation in terms of that, not we are just getting some kind of 3D shape, but we are also enabling just like rendering things of the 3D into the images from the arbitrary view. So we want to get this kind of the outputs. And yeah, so here basically the focus is slightly different with what we have seen in the previous lecture in terms of that now we don't want to just get some kind of the 3D, some shape, some geometric information. We really want to get some kind of the images from the arbitrary view. So that's kind of the main focus. And here also the interesting is that when we trained deep SDF kind of thing last time, that was kind of the case that we have the direct the information about this 3D shape. So we know for each of the query point, we know like which points are basically inside of the shape or the outside of the shape. So that was the case that we have some more the direct supervision in terms of the design distance are given or the occupancy are given. Here, the interesting is that while we also do some kind of the 3D reconstruction into the form of the implicit representation, now we assume that there is no 3D information. We only have the multi-view images. So the question is how we can do this kind of the 3D construction with the multi-view images. And here, so the thing is that now we're also going to assume that the camera matrix can be estimated using the algorithm that we discussed before, right? So the images and all the camera poses are given that how we can do some 3D construction. So I don't know like, how many of you have heard about the term of the NERF, the neural rendering, the kind of thing, the neural radiance field, which is like very famous, tons of the applications these days. Let me show some kind of one video for this. So this is kind of the demo of the library called the NERF Studio, which we're gonna also have the session to discuss like how to use this library. So this library might also kind of be useful for your rendering the contest, the project. So what you are now seeing is that we are basically seeing some kind of the reconstruction of the 3D scenes that has been achieved using the multi-view images in a way that now we can navigate the reconstructed space as we kind of like play games, right? And also we are placing some kind of some virtual objects, also with some kind of animations inside the reconstructed 3D scenes. So which means that now we can basically capture some kind of your own space or your the own object and combine them with some kind of some 3D models that's been used in the graphics and make some kind of the new applications or new VR, AR kind of the applications, which is basically very interesting techniques for the many kind of things. So this is basically the technique which is called the neural view synthesis. So here the basic idea is that when you have some kind of the fixed set of the images, the multiple images for the same object or the scenes that have been taken from the certain the camera the pose, how we can basically get the images from the novel view, from the view that we didn't take any photos from there, right? So this is the whole the idea, and there's some kind of the whole literature, more or less like 9 years for now, like that, people also explore like bunch of kind of things with some kind of the different representations for the 3D. So we are also not gonna discuss like all the things here, but I recommend you to check out all those kind of ideas. But if we go back to the basic thing, here the problem, the setup is that in the training time, we assume that we have a set of the multi-view images of the 3D object or the scene. And we also assume that the camera, the pose, the camera, the matrix for the all the images are basically given. So for your some real kind of a project, what you can do is that once you take the multiple images, I told you the library called the call map, which is structured from the motion the library. Also, there are many other libraries as well. Just you can use those kind of code to estimate the camera matrix or implement the 8-point algorithm yourself. Okay, so basically you can obtain the camera matrices. Based on that, what we want to do is that as the output, we want to get the implicit the 3D representation for the object or the scene. And the way that we are training this kind of the neural network, since we do not have some direct 3D information in this case, we do not know the occupancy or the distance for the point in the 3D space. So instead of like basically directly measuring this kind of discrepancy between the output, some kind of the 3D shape information, the 3D information that we have, what we can do is that we are going to render the 3D implicit representation into the 2D images for each of the view, and basically measure the discrepancy between the rendered image and the image that we have, and basically running some kind of the backpropagation. So in the inference time, what we are going to do is that given any kind of the camera matrix from the camera of the pose, it does need to be the camera pose that we have the images from there. It can be some kind of the random the camera matrix. And from there, we want to basically get some kind of the image from that view by rendering some kind of a 3D reconstruction in the output, which is represented as the implicit the function. Make sense? So this is the setup. There's something that may not be familiar with you might be that in case that if you didn't take the computer graphics course, how many of you have taken the computer graphics course before? How many of you have taken the computer graphics course? Yes. You can just type yes or no, whether you have taken the computer graphics or not. So if you took the computer graphics course before, that might be way better to understand all the things. In the case that you didn't take the computer graphics course, might be okay. We are going to get into some basics for that. So something here is that, I'm just talking about like rendering, right? Rendering is like some kind of a process that we are really making a 2D image by projecting things in the 3D into the image plane, right? So how we can do this kind of some projection of the like 3D information into the 2D plane in a way to get some kind of the realistic 2D image is all about the computer graphics. It's the whole computer graphics kind of the framework. So if you take the computer graphics course, you will see that like the whole course is about basically how we can do the rendering. Obviously, like the graphics involves like many other things, but the rendering is basically the basic process for that. Just like somehow projecting some 3D things into the 2D image plane. And so I mean, each of the slide here is like something that we can discuss over the entire semester. But some very brief kind of introduction for each of the things is that there can be two different ways. It's kind of very similar, but it's slightly different, some kind of the aspect. In terms of like, there can be some more like sort of the object-centric the perspective in terms of like, that for each of the point, in the 3D kind of things. Especially like in the graphics pipeline, we can assume that the 3D shape is represented as kind of the mesh, which means that we are having some kind of a soup of the triangles, some connected triangles representing the surface that we can consider like projecting each of the triangle into the 2D plane, right? And then all the information inside the pixel of the projected triangle can be calculated by interpolating some kind of the information projected for each of the vertex of the triangle. Yeah, we might also need to check some kind of some visibility test in terms of that, like when you have some multiple the triangles, like which triangle is like in front of the other triangle, right? So there are some kind of a bunch of the calculation in terms of like checking the visibility. But this is kind of like more sort of the object-centric idea in terms of that we project all the triangles in the 3D space in the 2D plane and do some kind of a calculation based on that. So this is the process we typically call the rasterization, like projecting things, and this kind of like interpolating things is the process of like rasterization. The other way around is more about like image-centric kind of the perspective in terms of that, not just projecting things into the 2D. Actually, we should ray from each of the pixel in the image plane into the 3D space. Shoot a pixel to the 3D space and see the first intersection point in the 3D space. And then we retrieve that information into the image plane. Actually, there can be more things that we can do in terms of that, there might be some kind of actually, this kind of the process is really kind of like simulating some physical, some kind of the phenomenon in terms of like the light traversal. So from we can basically model this kind of some lighting kind of things in terms of that the ray of the light is basically emitted from the light source and just traversing in the 3D space and just intersecting with any of the point in the 3D space and basically reflected over the surface and just like turning into the other direction and just doing this kind of the intersection with all the points in the 3D space. So we can really do this kind of calculation. Huge competition that we just like really shoot the ray from the light bulb kind of things in this 3D space and just calculating all the light traversal. Actually, we can do some kind of the reverse things, like starting from the image plane, shooting the ray in the reverse way, checking the basically intersection point, and just like following some kind of reflection kind of direction in terms of that when the ray arrives at the kind of the light source. So these are really some kind of like doing some simulation of the light traversal in the 3D space. So this is also kind of the very huge kind of area in terms of how we can do some kind of some accurate simulation with some kind of efficient computation. And this is also kind of the whole subject that you can learn from the graduate level, the computer graphics course. So there are basically two huge ideas in terms of like how we can do some kind of rendering from the 3D to 2D. But without like seeing any kind of details here, basically these are all the idea in terms of that we have some kind of some 3D information, which is typically represented as a mesh. Because as we have discussed in the previous lecture, mesh is the best representation to describe the surface, right? So we obviously need to have the surface information to do some kind of projection. But basically what we want to do is that from the multi-view images, we want to do some kind of 3D reconstruction and then render this 3D thing into some kind of a random view, right? So which means that if we could basically do some kind of a 3D construction into the form of the mesh, then it would be really good because then we can directly use all the rendering the machineries that have been used in the computer graphics, right? So what if we do some kind of a 3D construction into a mesh? Actually, there were some kind of the attempts to do that. So we discussed the idea like using the implicit representation, but what if we just directly reconcile all the things into the mesh? So like one simple idea for that is that like this kind of the idea, it's like 7 years ago, like in terms of like we start from some kind of the template mesh. Here the template mesh is some ellipsoid mesh, and over time with some kind of with the multiple images, we deform this template mesh in a way that the rendering of this mesh into the images into the view becomes like the same with the images that we have. This is really something we can do, right? But what we kind of the downside in terms of like reconstructing 3D things into the mesh? Can you see like what's the downside for that? Yeah, so basically there are a couple of some kind of the challenges, like when you directly want to get some kind of the measure as the output. Well, I mean, as you can see, the kind of biggest problem is that there are some kind of the limitation, the constraint in terms of the topology. Because if we want to make the like the chair here with some kind of the holes inside, and also the holes here, like some making some holes there, then which means that we need to tear the mesh, like cutting some part of the mesh and reconnecting some kind of the triangles, right? This would be involving very challenging kind of task, like how we can make the neural net to like tear some part of the mesh and just like doing some kind of the some kind of like connecting those triangles again. So this is really challenging kind of the task. So the topology might be kind of like one thing in terms of like getting some kind of the find the reconstruction of the outputs, and also it's really hard to get some kind of the precise reconstruction of the mesh because of the many reasons. One of the reasons here might be is that, as I said, the rendering the process is basically projecting the closest one into the image plane, right? So, and what we are going to do is that we are basically updating this kind of 3D things by rendering that 3D into the 2D plane for the 2D plane for the some arbitrary view and comparing this rendered image with the image that we have, right? So everything is basically done. The update the process is done in the 2D the image side. But the thing is that if we use the typically rendering the process with the mesh, which means that only the closest point will be basically updated, will be projected into the image plane and also updated through the backpropagation, which means that the update process will be very slow because only some kind of the visible area of the some kind of 3D object from each of the view will be updated for each of the images that we have. So that also basically makes another kind of the some challenges in terms of like making like faster convergence in the neural net training. So mesh representation has some kind of lots of issues with that. And also we have seen that input representation is kind of the best the choice in terms of getting some 3D the output as with the neural net, right? So we can, instead of like using the mesh, we can consider like reconstructing all the things into the signed distance function or the occupance function. But the thing is that when you use the signed distance function or the occupancy function as this 3D output, the challenge now also comes from that, how then we're gonna render the signed distance function. So in the case that when you have the mesh, it was more like straightforward. We just need to project all the thing and see which one is the closest one, right? So when the 3D thing is like represented as the function, then how we can render these things into 2D image? That involves some lots of issues, right? That we don't know how we can do that, right? But actually, there are some kind of ideas that how we can render implicit function, especially like signed distance function into 2D images. Can you see how we can do that? So if I go a little bit quickly with this, one simple idea is called the sphere tracing. So actually, the good thing of like having the signed distance function compared to the occupancy function is that every point in the 3D space, we have the information of the distance to the closest point over the surface. That's the meaning of the signed distance, right? So if we know that if that point is already inside of the object, then there's nothing we can do, right? So, but when we know that the point is like outside of the 3D object, the assigned distance function is giving the information about the distance to the closest point of the 3D surface, right? Then, which means that when the distance is d, if we make a ball at the point, and while taking that point as the center in the 3D space, that means that there is no obstacle inside this ball with the radius of the d. Make sense? Because if there were any kind of the obstacle, some point inside this ball, then the distance, the closest distance to the surface would not be d, but smaller than d, right? It's basically violating the meaning of the designed distance. So actually, this kind of thing, the designed distance is giving the meaning that, what's the kind of the region, the local region, that we can guarantee there's no obstacle inside this ball, right? So so this means that from starting from any point that we know is basically outside of the 3D shape, we can basically query the signed distance from this point. If that point is inside of the surface, there is nothing we can do. But when the point is outside of the surface, then we can make a ball like this. And we can march the ray along the direction of the ray until the point where the ray intersects with the sphere. Because we know that inside this ball, there is nothing, empty, right? And we can do the same thing, repeat the same thing by just querying the point, we're getting the distance, making the ball, and goes. Right? It goes until that we know that the point to the closest, the distance to the closest, the point of the surface becomes 0. So this is the very straightforward idea that has been introduced exactly 30 years ago. You can say that the long literature, like how long people have been used the implicit representation. So it sounds kind of like doable. So then, yeah, so we can try. Like we can just consider basically do some kind of 3D construction into the form of the implicit design distance function and render things using this pure tracing, this idea, and just like compare that output with the images that we have. So there were really some kind of the ideas, some kind of the framework that really does this kind of thing, like using this pure tracing for the rendering and just like comparing kind of with the outputs. But this idea also has some kind of some limitations. Can you guess what's kind of the issues with this? Also, a bunch of the limitations, like the first problem is that there are some kind of the repeating the process that we are basically advancing through the way with the amount of the distance that we are querying. This kind of like some advancing kind of the process is not differentiable. So how we can make it differentiable is kind of like one big problem. So there are some kind of the ideas how we can make it differentiable, but it still has some kind of issues with that. So that's kind of like one big problem. And also we don't know how many steps that we need to go, right? So it's really kind of the black box kind of things. Like, actually we just need like a few steps to reach to that the intersection point. But in the worst case, for example, like in this kind of case, so this might be really kind of the bad example that, we are shooting the ray, which is the parallel to the surface here. And as the ray is close to the surface here, actually this ball would be very small, which means that we will need to have lots of some kind of the point that we are basically, querying. While there's no intersection point along this way. So we don't know how much kind of the computation that we need to do to find kind of intersection point. So computationally too expensive, and also there are some issues with the differentiability. So these are some kind of the issues in terms of, either we can try to do some mesh reconstruction and then doing some kind of traditional rendering in the graphics pipeline, then the mesh reconstruction has lots of issues. But if we do some kind of the reconstruction with the implicit function, then there are some kind of issues with the rendering. So how are we gonna handle this kind of issue? So the kind of the known solution for now is that basically the conclusion for now is that still we use the implicit representation. But now what we are going to do is that we are going to slightly break the physics rule in terms of that while many of some 3D things that we are reconstructing will be solid object, now we are seeing everything is some kind of the volume in terms of that the ray can penetrate through all the objects. So that's kind of thing. So now we see like all the 3D objects is something like some fluid, something like the liquid kind of things, or some smoke kind of thing. In a way that the rays can pass through inside the object. Obviously, it doesn't make sense. All the objects, typically many of the objects that we are reconstructing, is not something like this. We just need to find the intersection point. But we are kind of like relaxing some kind of the physical rules in terms of that we make the rendering process to be much like easier without some kind of computation issues. And also we can update all the points along the ray. So it's not only updating like 1D intersection, the closest point, but we can update all the points along the way. So this actually can make the convergence faster. So because of like these kind of practical reasons, we are going to see some kind of the techniques that is based on so-called like relaxation of some physical rules, or actually violation of some kind of physical rules. So now we are going to treat all these really things that we are going to reconstruct as kind of the some volume, not the some kind of like something that we can like pass through. So this is kind of like interesting thing. And actually, more interesting thing is that this kind of the idea that we render some kind of volume is not something new. Actually, this is like really old idea that has been used in the computer graphics, some applications more than 40 years ago, 40 years. I mean, so that has been first introduced 40 years ago in the 1984, as you can see in this paper, very old idea. So lots of the people in the graphics have been trying to basically into some kind of techniques in terms of how we can render not the solid object, but some kind of the liquid kind of thing, fluid and the smoke, using some kind of rendering the pipelines. And there are like actually huge literature in terms of how we can do this kind of thing, lots of kind of things. Obviously, we are not going to get into too much details for that. But one thing that I'd like to say here is that so while these are some kind of the very recent technique, less than like 5 or 6 years or 6 years kind of old, in terms of like using some kind of neural rendering for the 3D reconstruction, the basic idea that we are using is actually very some kind of the well-established idea in the graphics pipeline that has been used more than 40 years ago. So based on this kind of the rendering pipeline for the volumes, we are going to see how we can do some 3D reconstruction with the multiple images. Clear? So for that, like, let me briefly get into some very basic idea. Actually, there are tons of some kind of the ideas about how we can do some neural rendering. But let me first briefly introduce like this earlier work, which is called the deep voxels, and see what's also the limitation of like this work. So here the basic idea is that we are doing some kind of 3D reconstruction while representing 3D with the voxels. But the voxels are basically not including any of the sign distance or the occupancy, but having some kind of the latent features that will be decoded using some kind of the neural network. So what we do is that we have some kind of the n number of kind of the multiple images with their the cumulative poses, reconstructing some 3D voxels with some kind of feature inside each of the voxel. So that's what we are going to do. So here so while there are also tons of the details here, if I just go very briefly for some kind of basic idea. So basically, let's see, this is kind of showing some kind of a slice of the 3D the voxels. So let's say like we kind of cut the 3D some kind of some big box in a way that now we see some kind of the 2D slice of the voxels, and also the 1D slice of the image. So this is kind of diagram showing the 1D to 2D, but obviously this can be extended for the 2D to 3D. Make sense? Like seeing the slice of the 3D in the 3D space. So we have the image here and some slice of the 3D the voxels here, like slice of the image and slice of the 3D voxels. And the high level idea is kind of straightforward in terms of that we somehow extract get some kind of the per pixel features for the images here, for all the multiple images, using some kind of the image encoder, using some convolution neural net. And then what we do is that we kind of like unproject the pixel features into the 3D space by shooting the ray from the image to the 3D space. So that's the kind of the ray casting the process, right? We shoot the ray from the pixel to the 3D space, and then just like copying these features into the 3D the voxels. The thing is that we're going to have the multi-view images, which means that like so some of the voxels also will have some kind of the ray coming from the different images, right? So for each of the voxel, there will be feature coming from the pixel in the first image and the pixel from the second image for the other images as well. So we need to do some kind of the integration of the features coming from different images. So that's kind of the process that we can do some kind of the pooling, or we can use some kind of recursive neural net like the GRU here, but this is not that important. So the point is basically we are integrating some kind of the 2D features coming into each of the 3D voxels, right? then in the inference time, in the rendering the process, basically what we can do is that it's also kind of the same thing. Now we just need to project all the 3D the features into the 2D pixel here, which means that we need to have some sort of some pulling the process, pulling all the features coming from the 3D the pixels on this ray projected to this pixel. Let me switch to ray. So if we see the ray here, for all the pixels on this ray, we just need to do some sort of the pulling to get the 2D feature here. Then we're gonna also have some kind of some features for all the pixels in the 2D plane for some arbitrary some random view. And then we just decode this using some 2D image decoder and get the images. So this is kind of like the whole process with some kind of very high level. One kind of a small thing here is that we can somehow consider some kind of the occlusion. So what that means is that there might be, if this voxel is basically visible, then the voxel behind this voxel should not be visible, right? So we want to introduce some kind of the notion of the kind of visibility, how visible each of the voxels are. So in terms of that, like what we can do is that the idea that has been introduced in this kind of old work is that we use some kind of some 3D convolution neural net in terms of like predicting some kind of the visibility score for each of the voxel. And this kind of the visibility score is used to take some kind of the weighted sum all the voxels. So which means that for each of the voxels that we have along the ray, we first basically predict some kind of visibility score for each of the voxel and taking the weighted sum of all the features here. So that becomes of the pixel feature in the rendering the process. So this is kind of like some very like high level the idea that sounds like reasonable in terms of the we do some kind of unprojection the projection from the 2D to 3D using the camera matrix that we have, right? And this idea was kind of like effective for many kind of the cases. So you can see that the left-hand side is showing some kind of some rendering the outputs while we smoothly move the camera in this 3D space. And the right-hand side are basically showing some kind of the images that have been taken in the 3D space, the input images, input the multiple images. So with some kind of the discrete set of the images that we have, you can see some kind of the smooth transition of the images when you move the camera in the 3D space, right? Looks quite good. And also, I don't know, maybe you can show some videos here. Yeah. So you can see that for those kind of cases that we are having some kind of very complex, some kind of the images here, like having all the characters over the surface here. Actually, we can see some kind of the very clean the outputs. See here, yeah. So these are the cases we have all the errors on the surface here. Especially like when you have the notion of the occlusion, the visibility, we can get some kind of the clearer results like this, while there are some kind of error cases in the other case. So sounds kind of like very impressive in terms of that we can utilize some like the camera model for the 2D to 3D mapping and this like some feature integration. Obviously, the downside of like this work is that it's basically the memory heavy. We need to have the 3D voxels, and each of the voxels we need to have some kind of the high dimension or some kind of latent feature. And there's no way that we can also increase the resolution. Once we have some specific resolution, that that's kind of the outputs that we get, right? So that's the limitation of the 3D voxels. But actually, the one more kind of problem of this is that actually the occlusion, the aware, the projection, the process of like getting the visibility is not physically correct. It's basically some kind of the very easy, some kind of the simulation, but there are some kind of issues with that. The problem of this is that there can be a case that the point behind of the other point can have the higher visibility, but it doesn't make sense, right? The point, so if we have some kind of visibility for some point that we have, the point behind the point should have the lower visibility, right? So it doesn't make sense that the point behind of something is like more visible than something that can block this point. But there's no such kind of some constraint that we can have in this case when you basically predict this kind of visibility using the neural network, right? So there can be some cases that the output might be physically wrong in terms of like getting some kind of the inconsistent the visibility, the occlusion kind of the quantities. So that's kind of the issues. So what we are going to see in the neural networks field is that we are going to make some kind of a framework which is slightly making more sense physically. So you can see that we are kind of breaking some physical rules a little bit in terms of that we are seeing everything as some kind of the volumes. But once we see everything as kind of some maybe not solely some kind of the volumes here, at least like we are going to utilize some kind of more physically collect some kind of the process, like rendering some volumes into the 2D images in a way that we can guarantee this kind of some kind of the physical rules. Okay, that's basically what we are going to see in the case of the nerve here. So the neural network field is kind of very similar with the deep voxels. The only difference is that now we are representing 3D things not into the voxels, but into the implicit function. We have seen like the advantages for that. And then instead of like the occlusion or the projection, like just predicting the visibility using the neural net, we are going to use some kind of more physically correct kind of procedure to determine the visibility. So we are going to see how we can do that. And also the thing is that while the deep voxels have used the latent features to determine the color with some kind of decoding the process, we are going to directly basically encode the color information. But we are going to see that it's kind of like the view-dependent color. So these are some kind of examples that we are reconstructing some 3D things with the with multiple images. So those are some examples like using 80 to 100 images from the multiple views, and you can see that it's very smooth in terms of like the images, getting the images from the any random views. And here one thing is that you might basically ask the question like why we get some kind of the view-dependent color. It doesn't kind of make sense. So here, without getting into also any details, we're gonna use the term of the radiance. So this is kind of some, precise kind of definition of the radiance. You can also check out some more details for this if you take the graduate level, the graphics course. But without getting into some more details, actually, roughly speaking, the term radiance is basically used as kind of the view-dependent color. Then why do we care about use the view-dependent color? Obviously, color is some kind of the inherit some kind of the attribute for the object, but the color still can vary depending on the lighting condition. So depending on the lighting in the space and depending on the view direction and also some kind of the reflection, the properties of the surface and many other things, when we render some 3D things into the images, depending on where basically we see that object, the color corresponding to each of the point can vary, right? You can see some kind of the highlight with the point here because like probably the light coming from here, this, while the object, the points over the surface of the object may have the same property, right? So basically, considering the view-dependent color basically means that we want to incorporate the information about some kind of the environment, the lighting, and many other things into the surface. But since we do not have this kind of the environment information, we just want to directly get the view-dependent color information. So that's the kind of the high-level the idea here, right? So basically, what we are going to do is that now we want to get the two implicit function. So we have seen like getting the one implicit function, right? Which is about the occupancy or the signed distance. Here we basically have the two implicit function, just extending like one more. Like one is the radiance map. That's basically the view-dependent color information. So since we basically get the view-dependent color information, we get not only the X, Y, Z coordinates in the 3D space, but also the view direction information, like some kind of the azimuth or the elevation kind of some information. So we have the two additional parameters for the view direction and the X, Y, Z coordinates for the color. And the other thing is basically something like the occupancy, describing the shape itself. But this is, you can see that it's not exactly occupancy, but opacity, also sometimes it's called the density. So we are also we're going to see the meaning of like this, what the occupancy means here. So we are basically going to train a two neural network to the implicit neural function One indicating the view-dependent color information, and the other one is basically something like the occupancy, but not exactly the occupancy. And one more thing that we are going to consider as some kind of the quantity described in this 3D shape is the transparency. So I said that the opacity is not exactly the same with the occupancy that we have discussed last time. So the meaning of the opacity is that, so basically we are shooting the rays in the ray casting kind of process in the image, like we shoot the ray from the 2D pixel into the 3D space. What we want to see is that when the ray stops by hitting some kind of the obstacle there, right? And since we consider some kind of the volume, actually we would like to take care about some kind of the probability, or like how likely the ray will stop at the point. You see the point? So it's not kind of like binary things. So that's why we call this as kind of volume. In terms of that, now we're gonna consider the probability of like how likely the ray basically stops at some certain point because some kind of the interaction with some kind of the point some kind of the object in this 3D space. Okay, so the opacity here basically indicates this kind of the probability of like how likely the ray will be terminated, stops at the point because some kind of some hitting some kind of object. Make sense? That's the definition of the opacity, which means that the output also should be in the range from 0 to 1. It's the probability, right? And the thing is that the transparency is kind of different thing. So when we talk about the opacity, we only care about the ray at the point, at a certain point, whether the ray will stop this point or not. But we also need to consider whether the ray will not basically stop at any point before this point. That's the transparency. So transparency is also kind of the probability in terms of like how likely the ray will basically fly over some kind of 3D space without basically intersecting any point in the 3D space. So how likely the space until the time t will be empty, not exactly empty, but not making any kind of the intersection of the ray with some kind of the obstacles here, while the ray is basically being advanced until this point. So that's basically the probability that we call the transparency. And actually, you can see that this transparency and the opacity should be related to each other. If there is no intersection until this point, that is basically some kind of giving the information about like how likely the ray will not stop until this point. So which means that actually the transparency should be computed from the information that we are getting from the implicit function of the opacity. So we are getting into some kind of the important slides, so it's almost the last minute of the lecture, but this is the most important part. So we are basically having this three notion, the radiance map, which is nothing but a view-dependent color, and the opacity, which is the probability of how likely the ray will stop at this point, and the transparency is like how likely the ray will not stop until like the time t here. Then based on that, how we can determine the color for each of the ray? Well, I mean, we can basically compute expected value. Expected value is basically something like for every event, we basically have some kind of quantity and the probability, how much the event will happen, right? So what we can do is that, let's say like we shoot a ray. Along the ray, there might be some kind of like infinite number of the points, right? For every point along the ray, what we want to calculate is basically how likely the ray will not stop until that point and then stop at that point. So that's basically the probability, right? So multiplying the transparency and the opacity. How much the ray will fly until this point without any intersection, and then basically stopping at this specific point. So that's the probability that we are going to multiply with the quantity that we have. So that's basically the way that how we calculate this expected value. And the probability is defined as some kind of the multiplication of the transparency and the opacity here. How likely the ray will basically fly until that point, and the stopping at this certainty point. And then we basically multiply this probability with the quantity that we have, which is the radiance, the color information. And if we accumulate all this kind of the multiplication of the probability and the radiance here, that becomes the expected value for the color along that way. Make sense? So for the neural radiance field, basically we are calculating, it's not just the neural radiance, it's a volume rendering. In the volume rendering, we just need the three terms: opacity, transparency, which determines the probability, and then the color view dependent color information, and taking the expected value to determine the color for each of the ray. And you can see that the transparency is defined in this way, taking the exponential of the minus of the integral like this. So we are going to see how we exactly get this kind of the formulation. But basically, what you can see, this formulation, we're going to see basically how we can derive exactly this formulation. But what we can see from this formulation is that first, this quantity goes from in the range from the 0 to 1, right? Because it's taking the exponential of the minus of something. And also, these are all the positive values because the opacity are basically positive values, right? So the integral like this should be positive, and this is the exponential of the minus some positive quantity, right? So for those kind of cases, we know that basically the graph should look like this, starting from 1 at the very beginning and going down to 0. So it makes sense first in terms of the transparency also becomes like the quantity in the 0 to 1 the range. Makes sense because it should be probability. And second, it starts from the 1. It also makes sense. At the very beginning, the transparency should be 1. There's nothing should be occluded, right? So it's also basically aligned with the physical concept of the transparency. The third thing is that you can see that also this quantity is basically being decreased over time. It also makes sense because this is the quantity which is corresponding to visibility in the deep voxels. So as you basically go further, the visibility cannot be increased. The transparency also cannot be increased. So we are basically modeling some kind of visibility in this way in terms of that it guarantees that the quantity becomes 1 at the very beginning and decreasing over time. It cannot be increased. And also make the value to be in the range from the 0 to 1. So you can see that it's physically making more sense compared to some random neural net that predicts the occupancy. And this is basically the formulation that has been introduced like 40 years ago, something like based on the volume rendering the equation. So, and you can see that we are basically having the two neural network, which is getting the occupancy here, and then the radiance field. And based on that, the transparency is calculated, and then we can determine the color for each of the ray. So this is the whole framework. And next time, we're gonna basically see how we can exactly derive this formulation, how exactly this formulation has been derived, and how we can really implement these things with some kind of a discretization, with some kind of a discrete samples along the way, and how we can do some kind of implementation of the whole this idea. And then we're gonna also and implementing this framework will be assignment 2. So we're gonna get into more details for that. Okay. Any questions on this? So while we discuss this part at the last moment of the lecture, this is the most important part of the discussion of the neural rendering. So I'd like to recommend you to check out more details for this. And we're gonna continue discussing these things next week. Okay. Please feel free to post your questions on Slack if you have for those kind of things. Okay. Okay, then I will see you next week. Bye.